In module 5.1, I introduced the notion of load strength interference. I defined two factors, safety margin and load roughness, that we would control and use to design to achieve a specified reliability. So safety margin corresponds to reliability. Load roughness tells us what spread in load would be acceptable in use environment. We are now going to mathematically derive those concepts, safety margin and load roughness. We're going to mathematically define them. We're going to see how they come about. And specifically, safety margin. That our emphasis will be more on safety margin than on load roughness. Load roughness is an equally important concept, but reliability is directly connected with safety margin, as we will see. All of the load strength interference analysis will use or assume normal distribution for load and strength, because that turns out to be very convenient, and not because it is that is what we expect, but that is very convenient. The math of load strength interference, the probabilistic design, becomes a little bit easier if you were to assume normal distribution. If you didn't have normal distribution, the same concepts still apply, but the math becomes a little bit more cumbersome. So analysis of load strength interference. Reliability is the probability that the strength exceeds the load. In other words, reliability is the probability that strength Y exceeds the load L. So I'll use Y to denote strength and L to denote the load. So reliability can be expressed in two ways, and I will elaborate on this in a second here. Can be expressed using the formula that you see here, where for each value of L, we ask the question, what is the possibility that strength would exceed that value of L? Strength Y would exceed that value of L. You could also ask the converse question. So if I'm given a particular load L, we can ask the question, for any given strength Y, we can ask the question, what is the probability that load would be less than the strength Y? Here we ask the question, given a load value, what is the probability that the strength would exceed the load? Here, given a strength value, we can ask the question, what's the fraction of load that is below the given strength? Okay, so you can pose it both ways. And F sub L here is the probability density function corresponding to load distribution, and F sub Y is the probability density function corresponding to strength distribution. So I'll show you how this is derived, how this can be used. So let's look at traditional design where load and strength are deterministic. Strength is Y and load is L. So design requires that L be less than Y strength. So what we do is, to account for uncertainty, what we would do is we will say that load should not be just less than strength, but it should be less than strength divided by a factor of safety. And this quantity is what we call as a factor of safety, and Y over N is what we call as the allowable stress. And the factor of safety accounts for all our uncertainty. Then we also choose worst case load. Okay, it's a deterministic design. So this is a deterministic design. In reality, the load is a continuous probabilistic distribution, but when we do deterministic design, we choose the worst case load, one value. To describe that load, and one value to describe the strength as well. So this is traditional design. And what we will do here in this course is probabilistic design. So we have a load distribution, and this is F sub L of L, and then we have a strength distribution, and that's defined by F sub Y of Y. And we have an at-risk population here, and we would like to figure out this at-risk population. So this, we don't know what it is. We would like to figure that out. So one way to do that is to choose an S value here, a strength value here, not S, Y. And let's say I have a differential interval dy. Then the probability that strength will lie between y and y plus dy is f sub y of y dy. By definition, right? This is by definition of what probability density function represents. So now the next, we can ask the question, what is the probability that load will be less than, so load will be less than y. Okay, that is L less than y. Okay, that again we can write as integral going from minus infinity to y f sub L of L dl. Okay, so if you were to call this event A, call this as event B, and then the probability that A and B will occur, that is, probability that strength will lie between y and y plus dy, and load would be less than y, is given by, this is the product rule, and you can assume these two are independent events, and that would give me a probability f sub y of y dy, right, times integral going from minus infinity to y of f sub L of L dl. So those are, and this is the reliability dr corresponding to a specified y value, specified strength value, and therefore the reliability would be my integral going from 0 to infinity or minus infinity to plus infinity, minus infinity to plus infinity of dr, okay, which is integral going from minus infinity to plus infinity f sub y of y dy, integral going from minus infinity to y of f sub L dl. Now you could pose the same question in another way. That is, alternatively, you could ask the question, probability that, what is the probability that strength will exceed L given a load and given a load value, and that's equal to integral, that's integral going from minus infinity to plus infinity of the load value dl, and integral going from L to infinity of f sub y of y dy. So, and now these two expressions are valid for any distribution. Because we have not specified what the PDF form has to be. Okay. So this is valid for any distribution. So now let's go back. That's how these two formulae are derived. Next, what I'm going to do is to define a new variable, little y, as being cap y minus L. And as we know, reliability is strength being greater than load, or y being greater than 0. And now we can use this to derive the safety margin, etc., that you see here for normally distributed load and strength. So in other words, you can, and I will do this, work this out, and show you how this comes about. So now we can, by looking at a normalized, a standard normal distribution of load, standard normal distribution of strength, you can now show that reliability is nothing but the cumulative distribution corresponding to the safety margin. So the reliability is nothing but the cumulative distribution, which is denoted by phi. Remember, when we denote a variable in standard normal distribution, we use phi to denote the cumulative distribution function. The cumulative distribution function of this quantity, which we defined earlier as a safety margin, turns out to be reliability when the load and strength are normally distributed. We'll derive this from first principles next. So we're now going to define little y as cap y minus L. Okay. And reliability, which we denote as R, is the probability that little y would be greater than 0. Okay, or probability that cap y would be greater than L. So let's assume that cap y, L are normally distributed. Again, as I stated, this is an assumption of convenience. Otherwise, the formulae that we derived earlier are still valid. These formulae that we derived earlier are valid even for non-normal distributions. But in our case, let's assume them to be normally distributed, because the math becomes simpler. If you didn't assume normal distribution, then you can still work out and calculate reliability, but the math becomes more involved. Okay, so let's assume that they're all normally distributed. So we know from reproductive property of normal distribution, what that says is y, little y, which is equal to cap y minus L, is also normally distributed. And that is the reproductive property of normal, by the reproductive property of normal distribution. These are the kinds of properties that are helpful for us. So now the standard normal variable of y is, we're going to call the standard normal variable z, as we've done in the past. And that is nothing but y, little y minus y bar divided by s sub y being the standard deviation of y. And reliability is the probability that little y is greater than 0, which is the probability that z is greater than, y greater than 0 would mean z has to be greater than negative of y bar over s sub y. And so now we can ask, what is y bar? What is y bar? Y bar is expected value of strength minus load. That's expected value of strength minus expected value of load, because expectation of sum is sum of expectation. That's equal to the mean value of strength minus the mean value of load. Okay, next we can ask what is variance of y, and that's s sub y squared. We know that's equal to variance of strength minus the load. That's equal to variance of strength plus variance of load, okay, which we call variance of x plus or minus y is equal to variance of x plus variance of y for independent x and y. Okay, so therefore, this is something we learned in expectation and variance. So therefore, variance of y is nothing but s sub y squared plus s sub l squared, and that in turn implies s sub, this is cap y, s sub little y is s sub cap y squared plus s sub cap l raised to the power 1/2. Okay, so therefore, as we defined before, let's call this equation star. So now substituting in star for y bar and s sub y, okay, we get reliability equals probability that z would be greater than y bar divided by negative of y bar divided by s sub y. That's equal to the probability that z would be greater than negative of y bar minus L bar divided by S sub cap y squared, S sub cap L squared raised to the power 1/2. And that is nothing but, by definition, that's nothing but probability that z would be greater than negative of safety margin. And that's defined as y bar minus L bar divided by S sub y squared plus S sub L squared raised to the power 1/2. Okay, so probability that z greater than negative of safety margin, remember from the standard normal distribution, that's equal to probability that 1 minus probability z greater than negative of safety margin would be equal to probability that z is less than or equal to safety margin, okay, plus safety margin. How is that? Well, let's draw the standard normal distribution. So let's say this is my negative safety margin, this is my positive safety margin. So this probability is the same as this probability. This quantity is 1 minus phi of safety margin. Okay, so what we want, so this is phi of safety margin, negative of safety margin. So what we want is probability that z greater than negative safety margin is 1 minus probability that z less than or equal to negative of safety margin. which is equal to 1 minus 1 minus probability that z less than or equal to plus safety margin, which is equal to probability that z less than or equal to safety margin, which is our CDF corresponding to safety margin. So that's how reliability turns out to be, the CDF corresponding to safety margin. So that is regarding analysis of load strength interference, the math behind it. As you can see, again, to recap, the math is valid. The definition of reliability is valid for any distribution. However, it's much more convenient if your strength and load are distributed normally. Then we can define safety margin in the manner that we have done. So we define safety margin, and we can also estimate reliability as this cumulative distribution function corresponding to safety margin. So this concludes module 5.2 for analysis of load strength interference. Next, what I will do is to work out a detailed example for load strength interference. Thank you.